Hello everybody and welcome back. We are getting to the core of the first idea in what are really two chapters that are one chapter. Chapters 4 and 5 really are one big chapter. And I've kind of been going between them, talking about heat. And we ended last class talking about Thompson's studies involving cannon boring. This is back in colonial times. As I mentioned, when you make a cannon, you cast it out of iron. You all know what a cast iron skillet is like. It's got that very rough finish. That has to be machined off for you to use the skillet. The inside has to be smooth and the outside bottom does too. Well, for a cannon, you have to smooth the inside of the cannon. And what he found, well, he didn't find it. What was known was that when you bored out a cannon, you essentially drilled it out. And in that process, tremendous amounts of heat were produced. They had to pour water over this. And in the machine shops, even today, you will see coolant sprayed onto the drill bit and the work to cool it down. Mainly because you'll either damage the work or the heat that's built up can heat the tool until it's red hot and it can ruin the tool. And as a machinist, I can tell you those tools are really expensive. 20 bucks a bit, 30 bucks a bit, $50 a bit. You can blow 50 bucks just like that, so it's cool. According to the caloric theory, all of this heat was already in the cannon and simply released when the boring process took place, because you went from solid metal to little metal shredded filings. Little pieces of metal. They looked at that as a change of phase. Now it turns out it's not. But nonetheless, back then, 200-300 years ago, they looked at that as a change of phase and therefore said, well, all of that caloric was already in there and it's released. Thompson didn't agree. Thompson said, look, I think that I could produce heat forever. He says there's so much heat coming out of this thing that he can't believe that it's already in that metal. He cannot believe that. So he actually constructs, he takes a small cannon and he bores it out nice and smooth, and what he makes is a tight-fitting plug. A smooth piece of metal that fits inside, and he turns that. And you can adjust the tightness of that, so you can make it hard or easy to turn. And you even lubricate this. He puts oil on this. And what he finds is that even though you're not actually boring it out, if he turns this hard enough, he actually has an assembly that uses 4 horses. He has a turnstile that has 4 horses turning the gear, so it's 4 horsepower. He's putting into turning this thing. He can actually boil water with it. No one had ever seen that. He could actually get it hot enough to boil water. People could not believe it. They knew you got hot with friction. They didn't think you could get, red hot. And he argued that in this case, there wasn't any real wear and tear taking place. And so he argues that the heat coming out is not being released from inside. He said, rather, the work that is being done to turn this thing is being converted into heat. And as long as he cranks it and turns it, heat will be produced. Now, the trouble is, the caloric proponents said, no. If you look at the oil here, if you look at the oil that's in here, the oil will turn black, and if you look at it carefully, you will find metal chips in it, little tiny flakes of metal. So he argues, no, you're still wearing down the metal. You're still releasing caloric. All the caloric is already in there. They don't believe that the work is being converted to heat. That means you are creating caloric. You can't create caloric. According to the caloric theory, you can move it around. You can't create it. And in this experiment, it seemed like it was being created. They said, no, no, no. It just shows you how much caloric is really stored in that metal. That's all. There's a lot more there than you thought. So the question is, how can you create friction yet not have anything worn down? If you can do that, then you can't argue that there's a change of phase, and you can't argue that there's a release of latent caloric. So, he can't work it out, but a contemporary of his, James Joule, is the next one near the middle of the first part to the middle of the 1800s. He hits on the idea of generating friction using liquid water. Stirring water, essentially. He builds, it's complicated, there's a nice diagram of it in the textbook, but essentially I'm just going to stylize it. You have a container of water with a stir in it that can agitate and stir the water. So you agitate the water. His was much more complicated than this. Furthermore, he had a thermometer in this, and this is one of the things that had to be advanced. The temperature changes that you get here are rather small. So they had to develop thermometers that were sensitive enough to see that change, which essentially means if you have a glass thermometer, the smaller you can make the hole, then the more sensitive the thermometer is. It's hard enough to just make a glass tube with the hole down the middle, but to make it even thinner, that's craziness, okay? But they did it. And here is the genius. He not only stirred it, but he came up with a way of stirring it a specific amount. He would have a rope that would come over here, and then he had a weight. And he would allow the weight to fall down. I think the story is he did this from the second story of some building. They didn't have more than 2 stories way back then. They didn't have steel to make skyscrapers. The point is, he could stir the water, he could agitate the water a specific amount in a controlled manner. He didn't just turn the thing and have it go. He had it turned a definite amount that could be controlled. You could control it by the size of the weight and also how far the weight fell. When the weight falls, gravity does work on the weight, and since the direction of gravity and the direction of fall are the same, positive work is done. So he can allow definite amounts of work to be done on the water. And what he found, the most important thing he found, and we should draw something else too, this is all insulated. Back then you'd use feathers or whatever. Nowadays you could use styrofoam, but it's all insulated so that no heat can flow in or out from the outside. The only thing you can do is to stir the water. And the most important thing that he found was that the stirred water was warmer. Stirring the water raised its temperature. Now this is all greatly simplified, as we always do. So stirred water was warmer And that meant that caloric was created, because I don't care how much you stir the water, you're not going to produce little water chips or flakes of water, or you're not going to change the phase of the water. So you can't argue that there's a phase change and release of latent caloric. Instead, caloric had to be created. And that violates one of the basic principles of the caloric theory. And it disproves the caloric theory. It disproves the caloric theory. Furthermore, what he finds is if we make a graph of the work that is done versus the change in temperature of the water, he finds that there is an exact linear relationship that if you double the amount of work, you will double the temperature rise of the water. Triple the amount of work, you will triple the temperature rise. Do 10 times as much work, you get 10 times the temperature rise. Since work is related to energy, the ultimate conclusion here from Joule's experiments is that heat is a form of energy. Now we'll take a look at, and this is true by the way, this is true. It is a form of energy. We will take a look at exactly what kind of energy it is. But for the moment, I want to talk about the ramifications of this. If heat is a form of energy, for example, in this room, this air is reasonably warm. It's certainly warmer than it is outside. If heat is a form of energy, then what can you in principle do with the heat? What is energy? What did we say energy was? Look it up. What's our operational definition of what energy is? Go look it up in your notes. What is it? We have potential energy, kinetic energy, we've got radiant energy. What does energy ultimately transfer or translate into? Real loud.
The ability to perform work.
The ability to perform work, which translates into the ability to apply a force through a distance. That means somehow, if you know how to do it, since this room is full of heat, that you should be able to use that heat to cut a plank of wood, to pump water out of a mine, to move a vehicle, to lift something up, to turn a machine and something. It means that heat can be used to do work. Now nobody knew how to do that. But the implication is, how hard is it? You tell me, what do you have to do to get heat? What do you do? Well, let's say if you don't have electric heat or solar heat, what do you do to heat your house? Huh?
Make a fire. Make a fire.
You make a fire. Make a fire means you got to have wood, coal, peat, natural gas, a fossil fuel. Well, technically wood is not a fossil fuel. But all you got to do to get heat is burn something. And hell, there's stuff to burn all over the place. When people start to realize this realization in the first half of the 1800s that heat has motive power, that's how you would say it, it has the power to move if you know what to do with it, that the heat can be used to perform work. Heat is energy. And what has happened as a result of that is that For instance, before this was understood, if you had a mill, does anybody know what a mill does? You've probably heard of millstones and down the old mill stream, and there are many people, including this class, who have a Mr. or Ms. Miller in them. Every town, every little village had a miller. What did the miller do? Anybody know? I mean, you may not know now. Yes?
They ran the mill.
Okay, they ran the mill, but what did the mill do?
Like windmill.
There was a windmill, so they used wind power. Is that the only kind of mill there was? What else could you power a mill with? A water mill, water wheel, and maybe animals. But what does milling mean? It means they ground up the corn and the wheat into flour. Flour is ground up corn. Okay, you can't take the kernels off the corn and make bread. Well, I suppose I don't know. Actually, you can. But what you do is you dry the corn, you take it to the miller, you pay him some money, and he'll grind it into little fine powder. Then you can have cornmeal. I love cornmeal. Cornmeal and chili. Oh, cornmeal and chili. That's just, yeah. Okay. If it was wheat, you take the wheat grains to the miller. He mills it down into this white powder. And you can make bread, and you can make muffins, and all kinds of stuff from that. But you can't just take the grains of wheat off the field. They have to be milled and ground down into a flour. So you have corn flour, wheat flour, and there's other flours available too. And so it used to be that you had to have a waterfall or a windmill, like they have in Holland and Greece and places like that. Or you could have animals. The paddock that Thompson used was not normally used for turning cannons uselessly and boiling water with a piece of metal. It was used to run a mill. Or, for instance, if you had a carpentry shop, a lot of the work was done by hand, okay? But if you had a source of power, like a windmill or a water wheel, you could have a saw that could cut lumber into boards and so on and so forth. So you had to have the mill or the saw mill, right? A saw mill. You had to have it by water or by wind or whatever. But now, if you could figure out how to use the heat to perform the work, you don't have to have a windmill. You don't have to have a water wheel. As long as you got stuff to burn and some water to boil, you can use a device called a steam engine to run your mill or your carpentry shop or your faculty. So it was the discovery that heat is a form of energy that allowed us to release huge amounts of energy, particularly from fossil fuels. And that led to something called, what change in society was that? The steam engine we're going to be talking about at great length. But the steam engine was the source of it. This was a huge change in society. What do we call this revolution? The Industrial Revolution, which among other things created the middle class. Before the Industrial Revolution, there were two classes, the filthy rich and the filthy poor. Sometimes it seems like that's still the case, right? But actually, you look at how we live, I think most of us are the middle class. Not all of us, though. Not all of us. But there were the nobility, and then there was the reek of the earth. And it made no color what your skin was. You were either filthy rich or you were filthy poor, and that's how it was. You couldn't even afford a set of glasses for your kitchen. You couldn't even afford that. But when the Industrial Revolution came in, you look at, for instance, making a piece of furniture, making a table. Before the Industrial Revolution, you had to hack by hand all the boards, or you had to use wind power, which is limited. To make the boards, and everything had to be hammered by hands, trying to even make nails. How do you make nails without machines? I mean, think about it. How do you make a nail? How do you make a nail? So furniture was really expensive. Toys, really, really expensive. You didn't have toys, the nobility had toys. Everybody else barely eked out a living. But when we found out how to use heat to run factories, we could use machines to do that. We could make a machine that could make 1,000 nails every 10 minutes or something and crank them out. Much faster than a windmill-powered machine could do it. You had a carpentry shop with a saw powered by a steam engine. You had several saws powered by a steam engine. And now you could cut many, many boards, and you could cut 5 boards at a time, and you could be making 5 tables at a time, which means the cost of the table goes way down, which means that some of the people who weren't nobility could start to afford that table or the tableware. And the factories came in. And when the factories came in, powered by steam engines, powered by heat, people went to work. And people worked in those factories, maybe not under the best conditions. Children in particular were really, really abused. And workers were completely abused. You know, you got your hand ripped off, your arm ripped off in an accident in a factory because of safety concerns. You were considered stupid, your family had to move out, it was your own fault, and that was it, they could have cared less. Nowadays it's very, very different. But nonetheless, on the average, people could afford things. People could afford glassware. People could have many, what we would think of as basic things like blankets. Even a blanket had to be a quilt, had to be sewn by hand, right? But if you're a weaver with a loom, instead of ka-chunk, ka-chunk, you go to a factory powered by a steam engine, jump, 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 and out comes this fabric that's even better than what you made by hand, and now you could afford blankets and so forth. This led to the Industrial Revolution, but in the end, the Industrial Revolution, we use so much energy now. I mean, we burn kerosene in airplanes, we burn gasoline in cars, we burn oil to generate electricity. What has happened is we have burned so much stuff. Burning releases what gas? What does burning release that's causing the problem here? Carbon dioxide. And what we do as human beings, I'm guilty, you're guilty. Whatever we do it too much. You figure, oh, what the heck? One little factory burning some coal, making some lumber. All right, you know. But then you got a huge factory making furniture for all of Europe. It turns out now you're burning 1,000 or 2,000 times the coal, and you got 100 factories. This one's making glassware, this one is making railroad parts, this one's making all of this burn this stuff. What we have done in the last 300 or 400 years is almost completely burned all of the fossil fuels in the crust of the earth. Because once we discovered that heat was a form of energy, we could get it by burning fossil fuels. Oh man, we just went, wow, we could move goods and so on and so forth. Everybody here love a beer? Everybody here love beer? Well, if not beer, some other kind of spirits, as they say. But it used to be, if you wanted a beer, you had to go to the pub. You could not transport beer. Beer spoils. Beer goes bad. They didn't have refrigerators. They didn't have ice either. You had to bring the ice from the mountains. Well, that required energy. But once the trains came in, you could transport the beer. And you could bring ice in from the mountains and fill a holder with ice and put the beer in there and keep it cold. And eventually you could use electricity and keep it in your house. All because that heat is a form of energy. All right? So this leads to one of the most important laws. We've seen the law of conservation of momentum. Momentum is conserved in all collisions. All collisions have the conservation of momentum. Let's go around here. Once we understand that heat is a form of energy, we'll explain eventually what it is, we now have the first law of thermodynamics. And this is simply called the conservation of energy. Whoops. We get to one thing this week. This is the thing we need to get to. Because the conservation of energy is the cause of a lot of the political strife and manipulations that are going on in the world. Simply said, the total amount of energy, not the individual amounts, the total amount of energy in an isolated system, is conserved. That is, it remains constant. There are various other ways of saying this, one of which is that you cannot create or destroy energy. You can change its form, but you cannot create it from nothing, and you cannot destroy it into nothingness. One of the questions we had earlier was what happened if we drop this hacky sack. Right now it has potential gravitational energy. If I let go of it, the potential energy is converted into kinetic energy. It speeds up. Right before it hits my hand, it's going pretty fast. And then suddenly, the kinetic energy is gone. And so is the potential energy. If it bounces back up, it goes back into potential energy. But if it just falls and stops, it loses the potential energy, it becomes kinetic energy, and then it would seem that the kinetic energy is gone. Well, it is, but not into nothingness. If you make careful temperature measurements of my hand and the ball after I catch it, you will discover that the temperature of my hand and the ball is higher. That the kinetic energy is not just destroyed, it's turned into heat. So when it falls, we have a conversion from potential energy of gravity to kinetic energy as it speeds up, and then suddenly the kinetic energy is converted into heat. And you can verify this. You can do it Joule style. You can pour water. You can take water at a certain temperature. Now you have to have a sensitive thermometer. But you pour the water into a container at a lower level, you'll find that the water is a tiny bit warmer. You've got to have a good thermometer. When the pendulum runs down, what's happening is it's colliding with air molecules, and the kinetic and potential energy that it has is being converted into heat. It's being converted into heat. Now, the next big idea is how do we convert heat back into another form of energy? That's called a heat engine, and we'll talk a whole lot about that. But let's just take a look at the energy distribution that takes place, say, in our country. Let's take a look at this room. Let's look at this room. All right. What kind of energy is coming out of these lights? What do we call that? Radiant energy, right? All right. What runs the light? Don't make this hard. Yeah, electricity, or as Arthur Weasley would say, electricity in Harry Potter. All right? The electricity, the electrical potential energy is converted into light. And the light comes into this room, and what happens to the light? Is it spilling out through the windows? No, it's not. A little is. A little is. But what if I close the windows and put black paper in the windows? What's happening to that radiant energy? The first law says it must be converted into some other form. Do we have any theater folks here? Do we have any performers? Have you been on stage?
I'm a stage manager.
Okay. What makes the stage hotter than Hades?
The lights.
The lights. Now you're using LEDs now, right?
You're LEDs.
You use the old incandescent lights,
We get really hot.
and it would get very, very hot. In this case, the light strikes this, it is absorbed, some of it bounces off, but ultimately all of the light coming out of these lights is converted into heat. And this is why, to a large extent, they put makeup on the actors, to keep them from sweating, or to keep them from looking like they're sweating. Meanwhile, they're miserable. There were some movies that were shot with lights that were so intense that the city lights of Hollywood would dim when they turned on the studio lights. They drew that much current. And ultimately, all of that electrical energy was turned into heat. We're going to see that heat seems to keep coming up, whether we want it to or not. Okay, so here at the end, we have heat. And then we have light, or radiant energy, in the room. Whoops. Well, the light had to come someplace. That came from electrical potential energy. All right, now, and we're going to debunk a huge myth that the politicians are going to try and foist on you. Okay? Where's the electricity coming from? If you trace these wires to the outlet, through the building, out to the poles, and trace them all the way back to the source, where will you wind up? A generator or a power plant, right? Now, you can go up on top of Savage Mountain, look down in the morning especially, and you can see this plume of steam coming up. That's the Warrior Run power plant. Okay? There's another one out in West Virginia, but ultimately, this comes from a generator. A generator, actually, we've got mechanical energy. Kinetic energy, rotational kinetic energy. So the electricity came from rotational kinetic energy, which is mechanical energy. What do you find that makes the generator turn? Around here. What's turning that generator? Come on, what's turning that generator? What is it? Okay, well, it is a steam engine. It's a steam turbine. It's not the choo-choo steam engine, but it's a steam engine. You have a steam engine. And the steam engine converts heat from the burnt coal into mechanical energy. Generator converts that into electrical energy. Light bulb converts that into the light. The lighted stuff, it becomes heat again. Where did the heat come from? What do they burn around here? Coal, which is chemical potential energy. You see, all we're doing is converting the energy from one form to another. All right, let's go back. I'm running out of room here. Where did the coal come from? What is coal? Okay, it's a fossil fuel. What do you mean a fossil fuel? What's a fossil? something that's old or whatever. Well, you go into a coal mine, I have, okay, and it's called a bump in the ceiling. It can kill a coal miner. It can kill a coal miner. It's a tree stump that's been fossilized and turned into coal. Coal is fossilized plants, okay? Coal is from plants. So you really haven't converted the energy, but plants that grew millions of years ago, covered up pressure, get turned into this wonderful substance called coal. What else can you convert ancient plants into besides coal? What's another fossil fuel? Oil, yeah. You go out to California, they don't burn coal in their power plants, they burn oil. You think of oil as just running your SUV or whatever. No, they burn oil. They also burn natural gas. All of that comes from plants and animals. Mostly plants, though. Well, what made the plants grow millions of years ago? The sun, which is radiant. You go back to the sun, you find nuclear energy. We could keep going back to the Big Bang or whatever. All that has happened is the energy keeps changing form into another form. Sometimes it's heat, sometimes it's not. That's all we're doing. It means all of the energy must come from some place. It's part of our society that we have successfully done is we have learned to take heat from whatever source, run generators and convert it into electrical energy, and then this is what's so cool, you can transport the electrical energy over wires, over mountains, over streams, and over valleys, and distribute it hundreds of miles. I mean, we are perhaps 50 miles away from some power sources here or more. It's unbelievable, but you can transport the ability to perform work over a metallic wire. Unbelievable. Now, not all heat comes from coal. If we stop right here, what other kind of power plants are there? Well, actually, let's start here. Mechanical energy can come from what? You see it on the mountaintops. Windmills. Are they? So you might also have wind energy. So wind could come in here, and hydro, gravitational solar could come in. Actually, with solar energy, you go right into, you could come in here and go with solar. Solar energy can directly provide electrical energy. Okay? Hydroelectric dams. But most of our energy is coming from heat from coal. Notice it all has to come from somewhere. And you tell me, if we need energy to survive, for instance, what is the source of energy for you? What do you personally, where do you get your energy from? Food. Food is plants. Where did that energy come from? The sun. So for the most part, the energy that you use in your body is the sun is stored in food. You eat the food, that runs you. But where does all the energy that goes into you ultimately go? Where does all that energy and all that food that you've consumed, what has it been turned into ever since the day you were born? Heat. Heat. You see, a lot of it winds up as heat. Where does all of the electricity that comes into this campus? We use a lot of electricity. It all comes into the campus. There's a big line that comes in and brings electrical potential energy in. And it runs elevators, and it turns on the lights, and it runs machines in our machine shop. But ultimately, what kind of energy form does it get turned into? Heat. Heat. We're going to see, this is going to lead to the second law of thermodynamics. That it seems like energy always wants to get into the form of heat. In fact, if you go to the power plant, is all of the heat from the coal converted into mechanical and electrical energy? It's not. How do you know that? What do you see outside? I just said you can see this from the top of Savage Mountain. What do you see coming up out of the Warrior Run? You see the water vapor coming up from the cooling towers. It turns out we're going to see that in order to convert some of the heat into mechanical energy, you have to throw some of it away into the environment, and you cannot get around that. That's going to be the second law of thermodynamics. But the problem now, this is a good way to end, is that we have been relying mostly on this road. This could be coal, oil, natural gas, and so forth. Most of our energy comes from these fossil fuels over here. Now let's take a look at a common thing. Now, I'm not getting down on Amazon, but Amazon is now showing this commercial where it shows this guy who manages their electrical vehicle fleet. We're using electrical vehicles at Amazon, so we're going totally green, zero carbon emission, and so on and so forth. And you'll hear that, yes, an electrical vehicle has zero emissions. Is that really true? No. Because what do you have to do with the electrical vehicle? You got to charge it up with electricity. And where the hell do you think the electricity is coming from? It's coming from a power plant. And what are they doing at the power plant? They're burning a fossil fuel, most likely. You see? You'll hear about a hydrogen economy. We'll use hydrogen. We'll burn hydrogen in the cars. Well, it's true. When you burn hydrogen, you get water. Zero emissions. But you have to make the hydrogen from water using electricity. All of these technologies require electricity, and what they do is they move the pollution. You ever heard of what's a NIMBY? Not in my backyard. So I'll just move the pollution from the streets. We'll move it out there into Western Maryland where they had the power plants, and we'll dump it all out there, but there's nothing being emitted over here in the city. See, it's a fallacy. These things that supposedly use electricity, well, you got to make the electricity, and that means you got a nuclear plant. I should have added nuclear here. You could have a nuclear plant. That's what I wanted to add. Ultimately, there has to be a source of the energy. That's the essence of the first law, and there has to be some place it goes. Let's just look at one final thing. They've talked about, for electricity, they said, we can put solar panels in the Southwest, the size of the state of Massachusetts, cover an area of the desert the size of the state of Massachusetts or something, and we can generate 1/4 of our electricity from that. Isn't that great? So what you're doing is you're taking solar energy and converting it into electricity. Sure, that doesn't pollute. But what happens if you take 1/4 of the energy in the sunlight hitting the Southwest and take it out of that region and pump it to the cities or California or wherever where we're going to use it? What happens if you reduce the thermal energy that's going into the desert by 1/4? Is that going to change the climate? Oh, hell yeah. Yeah. So just keep this in mind. We'll stop here. Anything we do, when done to the excess that we usually do it, is going to have an effect. What if you cover an open area with windmills? Well, the windmills, the energy must come from somewhere. It comes from the kinetic energy of the wind or the heat in the air. Which means, again, you're removing energy from that portion and transporting it someplace else. And if you do that to a huge scale, you can affect the climate. So what's the real solution? use less energy. And why don't we do that? Aiden, why don't we do that?
Because they're greedy.
Because they're what?
Greedy.
Who is they?
Energy.
The energy companies. They don't want you to conserve. They want to sell you the energy, and the politicians want to be helped by the energy companies. We're talking about trillions of dollars global here. They want you to use that energy. They want lots of people because they buy lots of energy. They don't want you to use birth control. They don't want you to use controlling population. They don't want you to do that. Lots of people use lots of energy. They make lots of money. Let's leave it right there. Have a great weekend. Okay.